So my intention is to start looking at quantum algorithms. Now in order to do that, we need to do a slight digression, and that digression is that we need to upgrade our status from looking at a single qubit to multiple qubits. And looking at multiple qubits allows us the opportunity to also look at correlated states, the extreme version of which are called entangled states. We'd like to bring about the idea of entanglement, quantum entanglement as well, which is at the heart of quantum mechanics. So before we go directly into quantum algorithms, which is probably reserved for the next lecture, and I'm going to talk about the Deutsch algorithm, Grover's search algorithm, Peter Shor's factoring algorithm, the concept of quantum Fourier transforms. Today I would like to talk a little bit about multi-qubit systems. How do we represent these systems? What does the linear algebra look like? And a little bit about entanglement as well. Some people think that if you would like to pick up one property from nature which makes a system quantum and distinguishes it from a classical system, then that property is entanglement. So it's quantum entanglement that really is at the heart of quantum computing. So that's one point of view. So people ask the question, what is the quantumness in quantum? There could be different points of view, and it's a slightly philosophical question as well. But something which is totally undescribable by classical physics is entanglement. It's a correlation that defies classical descriptions, and it also violates some other preconceived notions about reality, which are called local realism. So it violates local realism. It makes quantum mechanics non-local, it makes quantum mechanics non-real. So before we start discussing these properties, so let me introduce a quantum gate on a 2-qubit system, and I'll build up from there. Suppose I have a NOT gate acting on a single qubit. Now I know that this NOT gate is represented by a unitary transform, which is 0, 1 here, 1 here, and 0 here. This NOT gate might act on some gate, on some state, and generate a new state, psi prime. For example, it can act on ket 0 to generate ket 1, it can act on ket 1 to generate ket 0. And we know that these states are also represented in the Zeeman basis, can be represented in the Zeeman basis. So there is a matrix for this unitary operator and a vector for the ket. So this ket is represented by a vector which has 2 entries. And let me just, for the sake of recollection, write down the 2 Zeeman basis states as ket 0 and ket 1. And they have this matrix representation. And in this representation, this is the unitary matrix for the NOT gate. Now, how do you choose the ordering of these elements in the unitary matrix representation? So generally the scheme that is followed is the following. These rows correspond to the 2 basis states. Now, and this is just a mnemonic. A mnemonic is a useful way to remember what element corresponds to what. ठीक है, इसको कहते हैं mnemonic. It's just a remembering aid. So the rows are identified with kets, and the columns are identified with the corresponding bras, which means that this unitary operator could be written in the following form: coefficient 0 with a device. I'm calling it a device because you haven't seen this before, at least in this course. A ket 0, bra 0, plus this element corresponds to coefficient 1 ket 0 bra 1 plus this coefficient 1 ket 1 bra 0 plus this coefficient 0 ket 1 bra 1. Now these terms just wither away because they are 0 being multiplied by something, and we left with ket 0 bra 1 plus ket 1 bra 0. So this is the unitary matrix corresponding to a NOT gate written in Dirac notation. And objects of this kind which have a ket followed by a bra, they are called outer products. An inner product, on the other hand, you've already seen inner products. An inner product is just a scalar. So in the inner product, you first write the bra, say some phi, and then a ket. This is a scalar, this is a number. And you can also verify this by putting this in matrix form. So if psi is, say, AB, where A and B are complex numbers, and phi is some vector CD, then this inner product can be written in the following form. You need to find the bra corresponding to this ket. So you take the transpose of this and the complex conjugate of the entity C star D star, and then this acts on ket psi, whose form is given by this, and you will end up, so now here a row vector is being multiplied by a column vector, and you will end up by a number, with a number C star A plus D star B. So this is a number, a scalar. It's not a matrix or a vector, it's a scalar. So this is an inner product. Here we have changed the position of the ket and the bra, and we find out that this object here, which is an example of an outer product, could be expanded in the following form. So I write the form for ket 0, which is column vector 1 0, and the form for bra 1, which is a row vector, which corresponds to the transpose of this thing. And if these were complex entities, I would also take the complex conjugate. Unfortunately, these are real numbers, so this is what you get. And now I have a column vector being multiplied by a row vector. Both of these elements are compatible for multiplication. So I do a straightforward multiplication, I would get this. So this outer product corresponds to a matrix. And this matrix has zeros everywhere. It just has one at one position, and that one position corresponds to this coefficient here. Likewise, this thing would be 0 0 1 0. Alright? So this is the outer product formulation of a unitary matrix. Now, question is, suppose I have an identity matrix. The identity matrix is also important in many cases. Could you write this in its decomposition of outer products, please? Very simply, this corresponds to ket 0 bra 0 plus ket 1 bra 1. This is the identity matrix. Likewise, you could write sigma y, which is 0 minus iota, iota 0 as the following. Minus iota ket 0 bra 1 plus iota ket 1 bra 0. So just remember that you have to order the rows as ket 0, ket 1, bra 0, bra 1, and it will be easy to remember all of this. So you put all of these rows in logical ordering 0, 1, all the columns in logical ordering 0, 1, and you'll be able to write this just by inspection. And it's very easy to really use this outer product formulation. For example, if you would like to find out what happens to the NOT gate when it acts on ket 0, you know that the answer is going to be ket 1, because the NOT gate inverts the basis state. We could also write this out explicitly in the following form. This state acting on ket 0 would result in, now if I take the inner product of 1 with 0, I'll get 0, so this term just goes away. This term gives an inner product of 1 and I'm left with ket 1. So sometimes this formulation, this outer product formulation of unitary operators is very convenient. Likewise, I can write Hadamard gate, all kinds of unitary operators in this fashion, in the outer product form. Okay? So generally it's also, if you come across this word that kets live inside a space which is called the Hilbert space, and the operators live inside a space which is called the Liouville space. So if you come across these terms, this is what this really means. So now we have an inner product and we have an outer product. Now let's do the following. Suppose I define a gate which is a 2-qubit gate. Now this is the first time I'm starting to look at 2 qubits. 2 qubits makes the quantum mechanics really interesting. Suppose I have a strange kind of gate, which means that I'm going to use a circuit model. So one line represents what's happening to one qubit. So this is the first qubit, and here I have the second qubit. And the kind of operation I would like to do is like a controlled NOT gate, which really means the following. Nothing happens to the first qubit, it just passes straight through, but the second qubit sees a NOT gate if the first qubit is in a particular state. And the truth table for this controlled NOT gate is the following. Now I need to have a way of writing 2 qubits, the states for 2 qubits. So suppose the first qubit is ket 0 and the second qubit is ket 0 as well. So I need to find out how do I write this in Dirac notation. But there are different ways of doing that. The most puritanistic way is to write ket 0 for the first qubit and put a small 1 here to show that this is the first qubit, and a small 2 here that shows that this is the second qubit, and put this sign in between, which is called a tensor product or a direct product. So that this is one mechanism of showing that these are the states of the 2 qubits. Now, in order to comply with some economy, you would also sometimes drop the subscripts 1 and 2, and you just assume that the first ket inside this combination corresponds to the first qubit and this corresponds to the second. Sometimes you wouldn't even like to write this tensor product, this O dot. You just write this as ket 0, ket 0. This is just for convenience. And sometimes you might also like to put this in a big ket, 0, 0. Now, what does the linear algebra for this look like? I know that the first qubit in this state is represented by 1, 0. This is also represented by 1, 0. Now, these are 2 by 1 vectors because it's a 2-dimensional space. The Hilbert space is spanned by 2 vectors. Any vector can be defined in a basis which is given by those 2 vectors, for example, ket 0 and ket 1. Any state can be written as a linear superposition of ket 0 and ket 1 with some complex coefficients. But now here we're talking about 2 qubits. So immediately the space becomes bigger. And in order to describe this 2 qubit space, we need 4 basis vectors. It becomes a 4-dimensional space. If there were 3 qubits, it becomes an 8-dimensional space. 4 qubits, 16-dimensional space. N qubits, 2 raised power n-dimensional Hilbert space. So the size of the space grows exponentially. And that's what gives quantum computing its power. You increase the number of qubits linearly or polynomially, the size of the space that you're working on grows exponentially. So with linear amount of resources, you can solve exponentially large problems. Okay, you want to do something that is really exponentially hard, like breaking an e-commerce code in an e-banking system. You need to only build a computer with polynomial amount of quantum computer with polynomial amount of resources. So this is the kind of parallelism that quantum mechanics offers. So the scaling of the size in which a quantum computer operates with the amount of resources that you put in is exponential. So how do I do this tensor product in linear algebra terms? First of all, I will make a bigger column vector. That column vector will now have 4 entries instead of 2. And if I just do this tensor product, this is the method to do that. You take 1, multiply this with 1 and 0. Then I take 0 and multiply it with the 4 things in the same order. So this will be ket 0 will be represented by this kind of column vector. Okay? Right. So first of all, I take this 1, multiply it with 1, and then I multiply it with this. I get these 2 entries. Then I take this 0 and multiply it with 1 and then multiply it with 0. I get these 2 entries, right? This is how you do it. Likewise, you could also figure out that ket 0, 1, which is the next in the sequence in a way. If you look at the binary code, 0, 0, then comes 0, 1, then comes 1, 0, then 1, 1. 0, 1 would be 0, 1, 0, 0. Ket 1, 0 would be 0, 0, 1, 0. 1, 1 would be 0, 0, 0, 1. And all of these states are orthogonal. So in 4-dimensional space, any quantum state could be written as a superposition of these 4 basis states. Correct? Or in vector notation, C naught naught, C naught 1, C 1 0, C 1 1. If the C's are complex numbers. G.
So can you repeat the double notation once more?
This which one?
The ket after 0 1 recover.
Ye wala? So this really means ket 0, the first state of the first qubit, and ket 1, the state of the second qubit. Are you getting this? Now, and if you want to make this state normalized, the sum of all these, the modulus square of all these C's must be 1. Alright? So this is the notation that we're going to work with. If we have 15 qubits, for example, you could just write this as, say, phi I tensored 15 times with some coefficient Ci. So you can just keep on doing tensor products. Alright, now let's figure out what's going to happen to the gates. So suppose I have a unitary gate acting on 2 qubits. So now if this were a 2 qubit state, I'm just using this psi here, it implies that I have a 2 qubit state. This psi is now a 2 qubit or a 4-dimensional vector. I would get a new state. I would like to ask, what should the size of this U be in matrix notation? How big should this matrix be? It's going to be a 4 by 4 matrix. So with n qubits, my Hilbert space, let's denote this by H, is going to be 2 raised power n dimensional, which means I would need n 2 raised power n basis vectors to describe any quantum state living in this bigger space. And the concept of block sphere also breaks down. There is no nice representation of a multi-qubit state. The block sphere only works for a single qubit. And the size of the matrices, or the size of the Liouville space, is 2 raised power n multiplied by 2 raised power n, which is really 4 raised power n. So you need bigger and bigger matrices. So for 2 qubits, you need 4n minus 1, sorry. For 2 qubits, you need a 4 by 4 matrix. In fact, you need a 4 by 4 matrix, but there are 16 elements in it. Alright? Now let's look at some examples. In order to look at what's going on here, let's consider the C0 gate. And let's write a matrix for this operation. Now this operation, by the way, if I just put a cloudy symbol around this thing, is a 2-qubit operation. It's a genuine 2-qubit operation. I could also have written another sequence like this, a NOT gate on the first qubit and a NOT gate on the second qubit. This is not a genuine 2-qubit operation because each qubit is independent and it's uncorrelated with the other. So this is just 1 qubit operations on 2 identical systems which are uncorrelated with one another. This, however, is a genuine correlated 2-qubit gate. Now let's first of all write down the truth table for the control knot. The truth table for the control knot goes as follows: 0, 0, nothing happens. 0, 1, nothing happens. However, if the first qubit is in a ket 1 state, the second qubit is inverted. So I get ket 1 on the first qubit and ket 1 on the second qubit. Likewise, if the first qubit is 1, the second qubit is inverted. In this case, I will get ket 1, 0. Alright, so now I would like to write down the matrix for this gate. And the ordering that I would like to use is, in fact, by looking at the kets that I've written in green at the top, it's straightforward to write down the matrix form. So I take the first basis element, 0, 0, and find what the output is. I supply the output 0, 0 in the first column here. Then I take the second input, the second basis state, and find what the output is. And then I write down the output corresponding to this matrix form corresponding to this output. I will get 0, 1, 0, 0. Then I take the third output in the order, find out what the output is, and I write the matrix form for this. I will get 0, 0, 0, 1. Likewise, I fill up the fourth column. So this is the control NOT operation expressed in matrix form. Yes?
So here 1, 0 transform to 1, 1 under which operator?
Under this control NOT operation. All of this is under the control NOT operation. So this is the truth table for the circuit that I've drawn over there. And this is the matrix form for the control NOT operation. So I'm inverting the second qubit, the target qubit, if the control qubit is in a state ket 1. Now could you kindly write down the outer product form for this? You just need to understand and remember the ordering. So these rows correspond to certain gets. So this is 0 0, 0 1, 1 0, 1 1, and these are the corresponding columns. So by looking at this mnemonic, this easy way to remember what element corresponds to what, can you please write down the outer product prescription of this gate?
In the matrix, the third column, are you sure that's 1 0? Shouldn't that be 1 1?
No. So let's write down the column vector form for this state, right? This is 0 1 tensor with 1 0. 0 0 1 0. Here 0 0 0 1. Why?
So 1 1 is.
Nee, what I'm doing here, I'm not writing down what this column vector is. I'm just identifying elements inside this vector. So this could be anything here. This could be A, B, C, D. This bra. So this, what I've written in blue, is a way to remember what element corresponds to what. So if I look at this element, say any element here, and suppose this were A and everything else were 0 inside this matrix, then this matrix would be A get 1 0 bra 1 0. That's what I'm trying to write here. So I'm not writing down this column vector which corresponds to ket 1 bra 1 0. This is just identifying the elements that go into this column. This is an easy way to remember what kind of outer product do I form. You get this? समझ आ गई बात? So is this making sense? The outer product prescription of the control NOT gate. Yes.
Sir, वहाँ पे 2-qubit gates वाले टॉपिक के अंदर जो आपने लिखा हुआ पहला ket 0 cross ket 0, नीचे आपने subscript 1 लिखा हुआ है. Subscript 1 का मतलब जो पहली लाइन में जो आपका control NOT है,
Yeah.
1 वाला ऊपर आएगा.
Right. So this is my first qubit and this is my second qubit. So this corresponds to, it's identifying the qubit. These are distinct qubits. These qubits could be at different locations. 2 ion traps inside, 2 ions inside a trap. This could be the first ion, this could be the second ion. These are 2 distinguishable qubits. So I have an outer product formulation for gates as well. This is the outer product formulation for the control NOT gate. Is this making sense? ये समझ आया? अगर किसी को नहीं समझ आया, I can repeat this. All right? No. All right. So now a control. This is a control NOT operation. By the way. No, but you just look at the matrix. There are zeros everywhere. You just pick the elements which are non-zero. So the top left is 1 here. So corresponding to that there is a 1 here, right? That one gives me, and how do you write the outer product? I look at the ket. This is in the first row, first column. This is in the second row, second column. This thing is in the fourth row, third column. Third row, fourth column. So each element corresponds to an ith row and a jth column. And the ordering, this is the first row, second row, third row, fourth row. So this is the ith row and this is the jth column. So you want to identify which of these ith rows do you pick and which of the jth bras do you pick. Of course, you can if you want to do the other one, but they're all 0. Now suppose I, just for the sake of it, I write identity ket 0 bra 0 cross with identity. Now I'm going to show you something, and I write ket 1 bra 1 and cross it with the sigma x poly operator. Alright, so just I'm going to show you something. So let's work what this thing is going to be. This is an outer product. Now this is your first encounter with an outer product being tensored with another outer product. Okay, which means a 2 by 2 matrix is being multiplied with another 2 by 2 matrix to give me a 4 by 4 matrix. So in order to can I multiply a column, a row vector with a column vector? I can do that because this has just, this could have 1 row and n columns. Whereas if this has n rows and 1 column, I can still multiply a row with a column. So in Dirac notation, this corresponds to a bra, this actually corresponds to an inner product. Okay, this is an inner product. However, it's also possible to first have the column vector followed by the row vector. Now this has n rows, 1 column. This has 1 row, n columns. And if I multiply this row vector with this column vector with this row vector, I'll get a matrix of size n by n. So I'll get a matrix n by n elements. Let's just hold on. This is really a column vector, therefore it is a ket. This is a row vector, this is a bra. So what do you don't figure out now?
I don't know how to write those 4 elements. What are we multiplying with what? So we could get those 4 elements. N elements.
So suppose, I will give you an example. Suppose I use this definition of kets. I can ask you to write any outer product. So what will this outer product look like? So this is my question to you. What will it look like? So I first write down the column vector corresponding to this ket, which is this thing. Then I write the bra corresponding to this 1 1. This will look like this. And see what happens. 0 multiplied with all of this gives me a 0. 1 multiplied with all of this gives me a 1. 0 0 0 0 0 0 0 0. So this outer product corresponds to this matrix. Now observe, ket 0 1. So I'm here in this row. Which column am I sampling? The last column. I'm sampling this column, and I sample this row and I sample this column, and look where the 2 lines intersect at this position. This position is non-zero, all others are 0. This is one example, okay? Now where was I? Alright. So if I look at this particular form, just this tensor product of outer products, let's see what this turns out to be. Let's call this sum x, big X. So this big X, let's see what it turns out as. Big X is ket 0, bra 0 tensored with identity. I write down this as a decomposition of outer products. Identity, you've already told me, is this combination of outer products plus ket 1 bra 1 outer product with sigma x. Sigma x is this polymatrix, ket 0 bra 1 plus 1 ket 0. Correct? Alright. Now what's going to happen here is the following. If I look at this outer product and I find the tensor product with this outer product, I can do this in matrix form. This is 1. All of this is correct. This thing is 1 1. So I first solving this in matrix form. Outer product ket 0 bra 0 corresponds to this thing, doesn't it? Identity is this thing. Outer product ket 1 bra 1 corresponds to this thing. The sigma x corresponds to this thing. So now let's do the matrix multiplication through the tensor product, to the dot product. Now how do I do this? I take this first element and then multiply it throughout with this matrix. And I get the first block here. Then I take the second element and multiply it throughout. I get the second block over here. Then I do this for multiply 0 with this thing. I get the third block. And finally, if I were to multiply this 0 with this, I will get the second block. So now 1 multiplied with this, I get 1, 0, 0, 1, and I get 0 everywhere else. Got it? So this is my new 4 by 4 matrix. Likewise, if I were to do the tensor product of this matrix with this matrix, I'll end up with, I have zeros everywhere, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, but this one, when multiplied with this matrix, I end up here. And now when I add these matrices, see what I get? Do I get the control NOT gate? I do get the control NOT gate. So the control NOT gate is actually this gate. One form of writing the control NOT gate is through this expanded simplification of outer products. The other method of writing a control NOT gate is more conceptual, which means that if your first qubit is in the state ket 0, then I write the outer product corresponding to that state, which is ket 0 bra 0. And this kind of outer product is really called a density matrix. I'm going to explain this in detail further. So you write down the density matrix for the first qubit when it is in the state ket 0, which is just the state written with its own bra. So if I were to take a state psi, ket psi, and write just immediately after it the corresponding bra, this also represents the state. This is another way of representing the state, but in a higher dimensional space, because this is now a matrix. This object here is called a density matrix. And it's often given the symbol rho. So I'm just going to describe density matrices in detail later, but for purposes of writing the unitary matrix, what I do, I break this down into conceptually. What if the first qubit is in the state ket 0? I write the density matrix corresponding to this, and if this is the state ket 0, what happens to the second qubit? Nothing. Nothing. Nothing means identity operation. Keep the second qubit as it is. And then I add plus sign, which is really OR. So if the first qubit is in the state ket 0, I do nothing on the second qubit. And if the second qubit is in the state ket 1, what do I do on the second qubit? I do a NOT gate. A NOT gate is really sigma x. So this sigma x acts alone on the second qubit. So it's a 2 by 2 matrix. And this is the density matrix for the first qubit, ket 1 bra 1. So when you take the tensor product of this first qubit state with what happens to the second qubit, I get a bigger 4 by 4 matrix. So conceptually, this is what the NOT gate is doing. If the first qubit is in the state ket 0, it does nothing to the second qubit. If the first qubit is in the state 1, it just inverts the second qubit, which is implemented by a Pauli operator sigma x. Got it? So now we have the facility of describing 2 qubit operations. 2 qubit operations are formed by putting together 1 qubit operations. And the good thing is that you can have a controlled linkage between what happens to 1 qubit depending on the state of another qubit. You can have controlled gates. And without these correlations between qubits, quantum computing will not be interesting. We'll just have single qubit gates which are totally describable classically. Now let's move back to the first example that I started off with. And then I'll come to the density matrix thing again. So now we have a matrix formulation for that controlled NOT gate. And we know what it does to different input states. But those input states could be anything. So you build a quantum computer that implements a controlled NOT gate. It can take any input whatsoever. You can initialize your initial qubit register in any state. It could be a superposition, it could be really anything. So now what I would like to do is the following. I make circuit. I extend this circuit to something more advanced. This is my first qubit line. This is my second qubit line. The Hadamard gate, you know, it has a truth table. It takes ket 0 and converts it into superposition 0 plus 1, and it converts ket 1 into 0 minus 1 with an under root 2 factor. And you already know what the controlled NOT gate does. So this thing here is a controlled NOT gate. This thing here is a Hadamard gate. First of all, let's write down the unitary matrix for this gate. Alright. So the unitary matrix for a Hadamard gate. What is this really doing? So the unitary matrix for a single qubit, let's call this H. We've already learned that this looks like this thing, 1 over under root 2, 1, 1, 1 minus 1. Alright, so what does, now suppose this is a 2 qubit gate, the 2 qubit gate. What is this gate doing? Can I write a form, an expression for this UH similar to this expression here. What is this gate doing to the first qubit? It's always applying a Hadamard gate. So the Hadamard gate has this. Suppose I write the unitary matrix for the single qubit Hadamard gate as H, right? What is it doing to the second qubit? Nothing. So this is the outer product representation of the Hadamard gate. It's really a 1 qubit gate hidden in a 2 qubit circuit because nothing is happening to the second qubit. This control NOT gate, you already know that what this does. If the first qubit is in ket 0, so I write the density matrix corresponding to it, does nothing to the second qubit. And if the first qubit is in the state ket 1, I write the density matrix corresponding to that state. It applies a sigma x operator or a NOT gate on the second qubit. So if I were to take all of this together and represent this by a giant unitary operator, remember a unitary operator is a rotation matrix. So if I put two rotation matrices one after the other, will I still get a rotation matrix? I will still get a unitary gate. The product of two unitary gates is also unitary. So the big giant matrix for this U is simply going to be this UH, which is now a 4 by 4 matrix. Right? So H is this thing. I take the tensor product with identity, I'll get a bigger 4 by 4 matrix. And if you have some software like Mathematica or Qiskit, and Abdullah is going to give you a lecture on Qiskit, you can easily do this matrix multiplication, even in Python. So the big U will be UH followed by U control NOT. Since this follows in time, my time is flowing in this direction. So I first have on the left the U Hadamard followed by the U control NOT. So this is the big unitary matrix for all of this. And you can all work this out as well. Sada product. You don't want to take a tensor product again. Now let's see what this state does. My question to you is, if I have this circuit over there, I call this an entangler circuit. What does this circuit do to ket 0, ket 0? So the first qubit is in ket 0, the second qubit is in ket 0, which is really first qubit ket 0, second qubit ket 0. I'm just factorized out the two qubits for ease, for your ease. What happens when the first UH acts on this? You don't need to do the matrix multiplication. You know what the Hadamard gate does. So can you create what the state is going to look like in this region just after the first Hadamard gate? You don't need to do a matrix multiplication. You can if you want. But here you can just look at the truth tables and find out what the new state is going to look like. Take your time, 2-3 minutes. Show it on your notebooks, please. Right, good. So you just get, so coming from this ket 0, a Hadamard applies to this ket 0, I get 0 plus 1. This just is where it is. Nothing happens to the second qubit, right? And I can write this in the following form as well. 0, 0 plus 1, 0, right? first qubit, second qubit, first qubit, second qubit, and a superposition of these two qubit states. Now I'm getting superposition of two qubit states. So the idea of superposition has extended to two qubits now. And you're not doing any measurement as yet. You're just letting the state pass seep through the circuit. You have input a certain state and you build this quantum computer or quantum kind of circuit and let the state seep through. All of this might take time because the manner in which you implement these gates, but nevertheless, now what you do after this state has been achieved, you come here and now you do your UC naught. Now quantum mechanics is linear. Linear algebra means linear algebra. It means matrix multiplication. When it acts on a single state, you get something. When it acts on the sum of two states, you get the sum of what would be if you would just input a single state. So now what happens if you act a control NOT operation onto this state? Give it a shot on your notebooks, please. What will your final state look like?
0, 0 and 1, 1.
By the way, if you look at two different ways, these are two different ways of writing the same state, right? Physically, it's just one state. I have an equality here. Physically, it's the same state. Now, the manner in which I write this state, I can always refer it back to some state on the first qubit. Tensor product with some state on the second qubit. That's it. So I can look at the first qubit. If I were to do a measurement, I look at the first qubit separately and independently from the second qubit. This is an example of what is called a separable state. So the two qubits live in their own worlds. I can do a measurement on the first qubit and on the second qubit, and they are independent. What happens on the second qubit does not affect what happens on the first qubit. Alright, so this state in between in the blue region is a separable state. Now, could you apply the control NOT gate onto this state, please? Muchibul? Right, so this is how I built the circuit. I built the circuit physically that the Hadamard only acts on the first qubit and nothing happens to the second qubit. It will remain 1. Yes. So it can take any input states. Okay? Now what is the output going to look like here? Control NOT flips the second qubit if the first qubit is in a state get 1. Alright, good. So at the end of this entire gate, I will end up with now, is it possible by looking, first of all, is this a superposition? Yes, it is. Second question, is this a separable state? Is it possible for me to factorize this into something on the first qubit and something on the second qubit? No, it's not possible. So I cannot write this as some psi on the first qubit tensored with some phi on the second qubit. I cannot write it in this fashion. It's impossible to do that. Correct? This is our first example of an entangled state. An entangled state is a non-separable state, and by so far we're dealing with pure states. An entangled state is a non-separable state. It cannot be factored out into a distinct state on the first qubit and a distinct state on the second qubit. You can't do that. In fact, this state is an example of what is called one of the 4 Bell states. Can you write other examples of states of this kind, please, which cannot be factored out into what happened on the first qubit and what happened on the second qubit? There are 4 such examples in a 2-qubit space, in a 4-dimensional space. That's not the only one.
सर जब हमने हेडरमॉन गेट अप्लाई किया था तो उसने हमें रिजल्ट में 2 क्यूबिट्स का एक सुपरपोज स्टेट दिया। तो जब ये कंट्रोल नोट अप्लाई होगा तो उसके बाद ही हमें 2 क्यूबिट्स का एक सुपरपोज स्टेट मिलेगा।
मिल गया।
तो मतलब उसको ट्रीट हम एज सिंगल स्टेट कर रहे हैं लेकिन बना वो 2 क्यूबिट्स नहीं बोलो।
Yes, it's the state of a 2-qubit system.
और जब किसी गेट पर अप्लाई करना है तो वो इंडिविजुअल हर क्यूबिट के स्टेट में जाके होगा।
In this case, this is acting on the first qubit, but this gate is a genuine 2-qubit state. It depends on a correlation between what's happening on the first qubit and the second qubit. This is not 2 1-qubit states. This is a genuine 2-qubit state, right? A controlled NOT gate requires 2 qubits. Another example of a gate which you might encounter is suppose you have 3 qubits. So what this gate does is that it applies a NOT gate on the 3rd qubit. If the first qubit is ket 1 and the second qubit is ket 1. This gate is called a Toffoli gate. Toffoli gate. One homework question is write down the matrix for a Toffoli gate in the outer product form as well as in matrix form. Yes, it will do nothing. So if you would like to write an outer product formula, let's keep that as a homework problem. Alright, so what are the 4 kinds of entangled states that you could write for 2 qubits? Right. So the 4 states are 0, 0, plus 1, 1, or 0, 0, minus 1, 1. Of course, with the 1 over root 2, because these are the complex coefficients. You take the modulus square, half plus half gives you 1. Again, the 2-qubit state, even though it's bigger in size, it also has to be normalized if you want to talk about physical reality, because these probability amplitudes correspond to probabilities when squared. The other 2-qubit states are 0, 1, plus minus 1, 0. In fact, these 4 states are called the Bell states. Bell states, in honor of John Bell. Generally, you denote these states by phi plus, phi minus, and these states by psi plus and psi minus. These are really important entangled states. The phi plus, phi minus, psi plus are also called the triplet states, and the psi minus is sometimes also called the singlet state. Yes. Okay. So my candidate state is, let's call it chi, is 1 over under root 2, 1 0 minus, this is just the same as this state. But that's already written there. So this is a global phase, so symmetry here. So these are the maximally entangled states. So these are the as big an entanglement as you can get in 2 qubits. These are entangled states and you cannot separate them out. Now, what does entanglement physically mean? By the way, quick question is, that gate that I've written with a Hadamard and a control knot is entangling an input. It's taking a separable state. The input state is ket 0, which is separable of course. It's taking a separable state and converting it into an entangled state. Can I ask you, how would you be able to create the other Bell states? So if you input ket 0, ket 1, you get another Bell state. But how do you get the other 2 Bell states? What kind of gate would you require? So think about controlled phase gates, controlled pi gates and so on. So this is another homework problem. So you could have a controlled NOT gate. You could also have a controlled pi gate. A controlled pi gate is simply, if the first qubit is ket 0, nothing happens to the second qubit. If the first qubit is ket 1, so you write the density matrix for this, the second qubit is sigma z. It's a pi phase shift. So with the help of these gates, you can interconvert between all the 4 Bell states. And you can also use different input states, but sometimes you do not have the luxury of creating the input states you desire. So you might have to interconvert between the 4 Bell states. And how can you undo this? Just a quick question, if I have this gate, this logic circuit, quantum circuit, here I do know that I am getting an entangled state. If my input would ket 0 here and ket 0 here. But I would like to disentangle. Right, so how do I make the inverse? How do I do the inverse of? Kiska Pell inverse? Can you draw a block diagram that does the inverse of this? How can I do that? Please try to attempt to draw the, in block diagram form, the inverse of this quantum circuit. Nice. No, inverse, no. What is the inverse of a Hadamard gate? Another Hadamard gate. Hadamard gate is self-inverse. What's the inverse of a control NOT gate? Another control NOT gate. So I have to do them in reverse order. Do control NOT gate followed by another Hadamard gate. So if you look at the matrix form of this, you have U Hadamard followed by U control NOT followed by another U control NOT followed by U Hadamard. And this is actually the inverse of this, because the control NOT gate is itself inverse. This gives me identity. I'm left with U Hadamard followed by U Hadamard. That's also identity. So I get identity. So this will create, this part is a entangler, this part is an entangler. And in fact, this is used for measurement. This is how you actually make. If you were, now why is this important? Do you understand this up to this part? Suppose I just remove this thing here, and I assume that the input to this state is 1 over root 2, 0, 0, plus 1, 1. I want to measure what the state is. I can use this circuit to measure the state. And for that I need to find out how is the entangled state different from other states. Now suppose in order to do that, any question up to this point? Yes. 0, 0 plus 1. वो 1 0 देता है. Alright, so let's look at what happens here. So if I have a control NOT gate here, let's see what do we get here. Starting from this input, I get 1 over under 2. Nothing happens here, but this is inverted. What is this really? This really is, so I factorize this out back again for convenience. So if I were to factorize this out, this is 1 over under 2. The first qubit is ket 0 plus ket 1 tensored with the second qubit is always ket 0. Got it? Now you do the Hadamard gate on the first qubit only. This gets back to ket 1, oh sorry, ket 0, and this is ket. Nothing happens to the second qubit, right? In fact, you could use the outer product notation and see how it scavenges on the input states. Alright. Yes.
What is the other, so there are like two inputs to this control NOT gate, one of the yellow but there is also another arm. What does that represent?
I do not understand your question.
I mean, the yellow state, right?
Yeah.
I mean, ये आपने ऊपर लिखा है.
नहीं ये पूरी की state है ये. This is the state that is going into this 2-qubit network. And the thing is that it's impossible to ascribe a state to the first qubit and ascribe a state to the second qubit. You know what is the meaning of ascribe? Let me say this in Urdu. ये नामुमकिन है कि आप इस 2-qubit state को देख के बता सकें कि फर्स्ट qubit किस स्टेट में है और सेकंड qubit किस स्टेट में है. नामुमकिन है. आप इस qubit के साथ कोई एक वाहिद स्टेट मंसूब नहीं कर सकते. इस qubit के साथ कोई वाहिद स्टेट मंसूब नहीं कर सकते. It's impossible to identify what state is the first qubit in and what state is the second qubit in. So, in an entangled state, you do not know what is the reality of a single qubit. You cannot ascribe a property to a qubit, which is a part of an entangled system. Just for the fun of it, can you write, suppose you have 3 qubits, can you write a maximally entangled state for 3 qubits? Three qubits, you want to write an entangled state for 3 qubits.
So, wouldn't that be Toffoli?
I mean, Toffoli gate can create this, but
So, I've made an example.
yeah, but write down the state. What is it? No. This is separate. So if I were to write and what factor should I write here? I don't know. This is an example of a 3-qubit totally entangled state. Right? So this is, by the way, called a GHZ state. Greenberger-Horn-Zeilinger state. Is this perfectly entangled? It's not perfectly entangled, it's partially entangled. Because you can ascribe a state to the first qubit here. Here it's ket 0, here it's ket 0, so you can write this as ket 0. But the second and third qubits in this soup of 3 qubits is entangled. So this is only partially entangled. So you have 3 systems A, B and C, and B and C are mutually entangled if I were to draw this diagrammatically and separable from A. This is only partially entangled. Yes.
Sir, is it possible कि जो second वाला बैठे हम सिर्फ उस पे describe कर सकें state का कोई ऐसी state?
हाँ, इसको go. Right? So this is hard to write. So what how I can write this as 0 0. This is the first and the third qubit plus 1 1, the first and the third qubit. Second qubit. So I just want to make mention that you need to specify. Right? So generally you don't write it like this, but this ascribes the state ket 0 to the second qubit, and the first and the third qubit are mutually entangled. So when it goes to 3 qubits, 4 qubits or more, the ideas of entanglement become blurry. I mean, you need to have different kinds of entanglement, different measures of entanglement. For 2 qubits is easier to define, and the possibilities also increase wildly if you have 3 qubits or more. Now, one question is about measurement. Suppose I introduce a measurement system. Now this is where the real fun part comes. So I'll take 5 more minutes for this. And I come up with an object. I've already talked about this kind of object, a beam splitter. What the beam splitter does is that when, say, a qubit comes in, this could be a photon or anything, but let's call this device a beam splitter. Could be a photon, atom, a generic device called a beam splitter. What this does is it gives me 2 outputs. One is a ket 0 output, the other is a ket 1 output, and I have detectors. Alright. Suppose I have 2 qubits coming in, and this is an entangled state, a Bell state. So a Bell state, a ghostly Bell state just comes into the 2 qubits. A 2 qubit Bell state is coming in, and I have 2 channels for the 2 qubits, and still I don't know what property does each qubit have, and then I put this beam splitter on the 2 arms or the 2 channels, right? And I put these 2 detectors right here. Okay. Now suppose I just don't do anything to this at the moment. I'm an experimenter, I just have 1 qubit in my possession, and the other qubit goes to some other person on a different planet or something. I don't know what's happening over there. Which means I really don't look at the second qubit. From my perspective, this second qubit is going into the dustbin. Right? I don't care about what's happening to the second qubit. Now when this single qubit which is a part of an entangled pair, is coming into me. So my name is Alice, the conventional terminology. So I'm Alice, I'm getting this one qubit which is a part of an entangled pair. And when I pass this qubit through a beam splitter, and I have these two detectors, what would I see? What would I see? Which of these detectors is going to click? इसका क्या मतलब? इसका क्या मतलब? हाँ, ठीक है, यही है इसका जवाब, लेकिन इसका मतलब क्या? It's a 50% probability that either the cat 0 is populated or the cat 1 is detected. So it's a 50% probability, let's call this channel A, let's call this channel A prime. There's a 50% probability that A is going to click and a 50% probability that A prime is going to click. And in order to check that this is a probability, I have to repeat the experiment many times. So I put in identical entangled pairs, identical copies of entangled pairs, because then I can build up a probability. Otherwise, I won't be able to tell what the probability is. If you have a coin, you want to tell whether it's fair or it's somehow fudged, it has heads on both sides. You have to repeat the experiment multiple number of times on identical coins. So I get multiple copies of these entangled pairs, and I operate my experiment. Half of the time this detector is going to click and half the time this detector is going to click. Just a totally random output. Totally random output. Got it? Totally random. So it's just like seeing a particle that has both possibilities, cat 0 and cat 1. Totally random. And if you look at if you want to learn a little bit about information theory, the entropy of this system is maximum. It's maximally disordered. It's totally random. Now suppose I am Bob, right? And I don't care about Alice. Or you are Bob and you don't care about me. So the kind of experiment that you would build is just throw Alice's qubit into the trash, and your qubit is now seeing this beam splitter and two detectors, and this is B channel, this is B prime channel, and you perform this experiment in a different part of the world, different part of the universe, and your output is also going to be totally random. So PB is the same as PB prime, it's going to be half. So you would say that my qubits are trash, they're random, they're totally random, there's no meaning to this, the entropy disorder is maximum. However, if both Alice and Bob have decided that we're going to make measurements at the same time, which means I get a qubit, Alice performs a measurement, Bob performs a measurement, and then a new pair comes in, Alice, Bob, and both of those measurements are synchronized. Mean an entangled pair comes in after every second, and we've decided that our clocks are synchronized and we're going to do measurement on the qubits that are arriving in synchrony 1 second after the other, and then we write down our outputs. So whether I'm getting 0 or 1, 0 or 1, and you write down your outputs, and I write down my outputs. I'm Alice, you're Bob, and then we converge we have a random in a coffee shop, and we bring down our strips of results. We find out that if this were my input state, this one, my inputs will perfectly match. Whenever I get a 0, you're also getting a 0. Which means that if Alice's detector A clicks, Bob's detector B clicks. If Alice's detector A prime clicks, Bob's detector B prime clicks. So our strips, our outputs, the sequence of bits that we are write down, zeros and ones, corresponding to our outputs. So Alice's outputs could on their own be totally random. totally random, disordered. Bob's outputs, and Alice doesn't know what Bob's outputs are because they're in separate parts of the world and they cannot communicate because they're so far away that it will take, the speed of light is our limitation. We cannot communicate our channel, so we cannot be over clever and share our results and fudge data. So Bob, that is you, will write down your outputs. Barring experimental imperfections, our outputs will perfectly match. Even though each, now this bit could have been 1, totally random. So looking at Alice on her own, I am a feminine character here, Alice, looking at on my own, I get a totally random output, total garbage. It's just a random sequence of bits, carries no meaning. Bob's sequence is totally random, but they're perfectly correlated. So if I were to get an output, I would be able to tell what Bob measures. Bob must have gotten the same result if I knew what the entangled state is. If the entangled state were 0, 1, plus 1, 0, I will still get total random gibberish on each of the Alice and Bob, but they're perfectly anti-correlated. So if Alice measures 0, Bob will measure 1, 0, 1, 1, 0. Correlation or anti-correlation, it's the same thing. So that's what an entangled state is. If you look at one part of an entangled pair, it appears totally random, which means you cannot ascribe a state to that single qubit. But when the two qubits are looked at together, there's perfect correlation. So the whole is not the sum of the parts. You're taking two random constituents, and when those random constituents are looked at in tandem, you get perfect correlation or anti-correlation. This is what an entangled state really is. And those two qubits could be really, really far apart. So suppose those qubits are on Earth and Moon. Doing something on the Earth immediately determines what's going to happen on the same experiment performed on Moon. What would the outcome be? And if there's no classical channel, there's no possibility of communication between Alice and Bob. So this is what an entangled state is. Now, armed with this idea, we can now start looking at quantum algorithms. Thank you very much.